At the heart of our galaxy, hidden behind veils of dust and swarms of ancient stars, lies something we cannot yet see with our eyes. Something that holds the mass of 4 million suns, compressed into a region smaller than our solar system. Something that bends light, warps time, and holds our entire Milky Way in its gravitational embrace. We call it Sagittarius A with an asterisk mark. The asterisk is a whisper of excitement, a marker of something extraordinary. It's a supermassive black hole. Not the blazing, violent monsters that power distant quasars, but something quieter, a sleeping giant, a patient darkness waiting at the center of everything we know. This is its story, and in a way, it is ours too. For most of human history, we couldn't see the heart of our galaxy at all. When ancient astronomers looked toward the constellation Sagittarius, they saw only a thickening band of stars, a bright swelling in the Milky Way's river of light. What they couldn't know was that they were looking toward home, toward the gravitational anchor around which our entire galaxy turns. Between us and that center lie 26,000 light years of space, filled with clouds of dust so thick they block visible light entirely. For centuries, this cosmic fog kept the galactic center hidden, mysterious, unreachable. Early telescopes could map the nearby stars, but hit a wall of darkness when they turned toward Sagittarius. It wasn't until we learned to see in other ways, in infrared light that can pierce dust, in radio waves that travel unimpeded through the cosmic fog, that the center began to reveal itself. And what we found there was stranger than anyone had imagined. The first hint came from an accident. In the 1930s, a young engineer named Karl Jansky was trying to solve a problem with radio static. He built a rotating antenna, some called it a merry-go-round, and listened to the sky. Among the crackle and hiss, he found something unexpected, a signal that rose and fell with a regular rhythm, not matching the sun's movement, but the stars. Something at the center of the Milky Way was speaking in radio waves. For decades, that signal was simply called Sagittarius A, the first radio source discovered in that constellation. As instruments improved, astronomers realized this wasn't just one source, but a cluster of them. And at the very heart sat something compact, intense, concentrated. In the 1970s, two astronomers named Bruce Bialik and Robert Brown gave it its unusual name, Sagittarius A, with the asterisk mark. The asterisk borrowed from physics notation for an excited state, a hint that this object was special, energized, different from everything around it. They didn't know yet what it was, but they knew it was important. The breakthrough came from watching stars dance, In the 1990s, two teams of astronomers, one led by Reinhard Genzel in Germany, another by Andrea Ghez in California, began doing something extraordinary. Using infrared telescopes equipped with adaptive optics to compensate for Earth's turbulent atmosphere, they tracked individual stars orbiting near the galactic center. These weren't distant, slow-moving objects. These were stars. These stars were racing around an invisible point at incredible speeds. Some moving at over 5,000 kilometers per second, fast enough to cross from Earth to the Moon in about a minute. One star in particular, called S2, became famous. It completes a full orbit around Sagittarius A in just 16 years, following an elliptical path like a comet whipping around the Sun. By tracking S2 and other stars over decades, measuring their positions with exquisite precision, astronomers could calculate the mass of whatever was pulling on them. The answer was staggering: 4 million times the mass of our Sun, all concentrated in a region too small to be anything but a black hole. For the first time, we were watching stars orbit a supermassive black hole in real time, not inferring its presence from distant galaxies, but seeing its gravitational fingerprints written in the paths of stars we could track individually, year by year, orbit by orbit. Think of it this way: gravity is the curvature of space-time. Near Earth, that curvature is gentle. We feel it as weight, as the pull that keeps our feet on the ground. Near a star like our Sun, the curvature is steeper. But near a black hole, space-time curves so steeply that it bends back on itself, creating a point of no return called the event horizon. At Sagittarius A's event horizon, about 12 million kilometers out from its center, 17 times the diameter of the Sun, space falls inward faster than light can climb outward. Once you cross that line, there is no escape. Not for matter, not for light, not for anything. All paths lead to the center, to the singularity where the known laws of physics break down. The radius of that horizon is called the Schwarzschild radius, named after Karl Schwarzschild, who first calculated it in 1916. It's a simple formula relating mass to size, but its implications are profound. Compress enough matter into a small enough space, and you create a region from which even light cannot escape. Sagittarius A holds 4 million solar masses within its Schwarzschild radius. All that mass, all that gravity, concentrated into a space that would fit comfortably between the Sun and Mercury's orbit. And yet, for all its mass, for all its power, Sagittarius A is surprisingly quiet. Most supermassive black holes of similar size are ravenous, consuming vast amounts of gas and dust, heating that material until it blazes with the light of billions of suns. These active galactic nuclei can be seen across the universe, beacons powered by black holes in their feeding frenzy. Sagittarius A is different. It barely eats. The material around it is thin, sparse, heated to millions of degrees, but too diffuse to produce much light. Compared to its more active cousins, our galactic center is almost silent, a faint whisper when it can be a scream. Why? Perhaps because the center of the Milky Way is relatively calm right now, lacking the dense clouds of gas that would feed the black hole more vigorously. Perhaps because the material that does approach is blown away by winds and magnetic turbulence before it can fall in. Or perhaps Sagittarius A is simply between meals, a giant taking a long rest between rare feasts. But don't mistake quietness for inactivity. Even in its subdued state, Sagittarius A occasionally flares. Sudden brightenings in X-rays and infrared that last for hours before fading. These flares hint at clumps of gas spiraling inward, or magnetic fields suddenly snapping and releasing energy, or perhaps small objects passing too close and being torn apart by tidal forces. Each flare is a reminder that the giant is not dead, only sleeping. Even black holes have rhythms of activity and rest. In 2019, humanity achieved something remarkable. We took a picture of a black hole, not Sagittarius A at first, but its larger cousin, M87, with an asterisk mark. The black hole at the center of a galaxy 55 million light years away. The image, a glowing orange ring around a dark shadow, became instantly iconic. Proof that we could see the unseeable. Image the edge of a region from which nothing escapes. But photographing Sagittarius A was harder, much harder than M87. M87 is larger and changes slowly, making it easier to capture. Sagittarius A, though closer to us, is smaller and more turbulent. The material swirling around it moves so fast that the entire structure changes in minutes. It's like trying to photograph a candle flame in the wind with a camera that needs hours of exposure time. The Event Horizon Telescope, a global network of radio observatories, working together to create an Earth-sized virtual telescope, spent years developing new algorithms to handle this change. They had to average thousands of rapidly changing snapshots, looking for patterns that remained consistent across the chaos. In 2022, they released the image. A fuzzy but unmistakable ring of light surrounding a dark center, the shadow of Sagittarius A's event horizon. It looked remarkably like M87, confirmation that black holes, regardless of size, follow the same fundamental rules. That dark center in the image is not the black hole itself, but its shadow. the region where light is either swallowed or bent so severely that it never reaches us. The glowing ring is emission from superheated gas orbiting just outside the event horizon, moving at significant fractions of light speed. Looking at that image, you're seeing the edge of darkness, the boundary between the knowable universe and whatever lies beyond. Rest in this achievement. We have seen the shadow of our galaxy's heart. What we still don't know could fill libraries. The image confirmed Sagittarius A exists and roughly where it sits, but it didn't tell us everything. We don't know exactly how fast it's spinning. Black holes can rotate, sometimes leisurely, some at nearly the maximum rate allowed by physics, close to the speed of light. The spin affects everything: how matter falls in, how space warps around it, how energy might be extracted from the rotation itself. For Sagittarius A, that spin rate remains uncertain. We don't know its orientation, which way its axis of rotation points relative to our galaxy. Is it aligned with the galactic plane or tilted at some odd angle, a relic of past chaotic mergers? We don't fully understand the magnetic fields threading through the material around it, though new observations using polarized light are beginning to map those invisible structures. These fields could be crucial to understanding why Sagittarius A is so quiet. Perhaps they act like a barrier, preventing much of the nearby gas from falling in. And we don't know what will happen next. Will it remain quiet for millions of years? Or could a large cloud of gas or an unlucky star pass close enough to trigger a feeding event, waking the giant and flooding our galactic center with radiation? Some mysteries deepen even as we learn more. Sagittarius A is not alone in being a supermassive black hole. Almost every large galaxy has one at its center. The masses vary. Some are millions of times the sun's mass, others billions. But the pattern holds. Black holes and galaxies grow together, their fates intertwined. How they form is still debated. Perhaps they began as seeds in the early universe, formed from the collapse of massive gas clouds, or the first generation of enormous stars. Perhaps they grew through countless mergers, smaller black holes combining over billions of years. Perhaps both processes played a role. What we know is that there's a relationship between the mass of a galaxy's central black hole and the mass of its bulge, the dense central region of stars. This correlation suggests they influence each other's growth. When a black hole feeds aggressively, it can produce winds and jets that push gas away, regulating star formation. When a galaxy forms more stars, more material might eventually fall toward the center, feeding the black hole. They shape each other. These giant structures, cosmic patterns in a dance that spans billions of years. Even the largest things in the universe are related, interdependent. 4 billion years from now, something dramatic will happen. The Milky Way and our neighboring galaxy Andromeda are moving toward each other. Not quickly by human standards, about 110 kilometers per second, but inevitably, in about 4 billion years, they will collide. Stars will pass through each other like ghosts. Space is so vast that direct collisions between stars will be rare. But gravity will reshape everything. The spiral arms will distort. Stars will be flung into new orbits, and the two galaxies will merge into a single elliptical galaxy. And at the center of that new galaxy, Sagittarius A will meet its counterpart, M31, with an asterisk mark, the supermassive black hole at Andromeda's core. Over millions of years, they will spiral toward each other, losing energy through gravitational waves, falling even closer. Finally, their event horizons will merge. In that moment, a burst of gravitational waves will ripple across the universe, space-time itself shuddering from the collision. What emerges will be a single black hole, perhaps 100 million times the Sun's mass, spinning from the combined angular momentum of both objects. The sky, for any world that witnesses it, will be extraordinary. Two glowing cores approaching each other, jets of radiation, waves of star formation triggered by the merger. A cosmic spectacle playing out over millions of years. Earth may not survive to see it. Our sun will be nearing the end of its life by then, possibly already transformed into a red giant. But the merger will happen regardless, reshaping our cosmic neighborhood into something new. Even galaxies are not permanent. Everything changes. So, what does Sagittarius A mean for us? What does it tell us about our place in the universe? It reminds us that we orbit something strange and profound. The Milky Way is not just a collection of stars randomly scattered through space. It's a structured system, held together by the gravity of its central black hole and the dark matter halo that surrounds everything. Every star in our galaxy, including our own sun, orbits that center. We're about 26,000 light years out, moving at about 250 kilometers per second, completing one orbit every 230 million years. The last time we were at this point in our galactic orbit, dinosaurs had just begun to walk the Earth. We are part of a galactic ecosystem, shaped by forces that extend from the center outward. Sagittarius A may be quiet now, but in its more active past, it may have influenced star formation throughout the inner galaxy, regulated the flow of gas, even contributed to the beautiful spiral structure we see in other galaxies like ours. It also reminds us how much we've learned to see. For most of history, the galactic center was completely hidden from us. Now we can photograph the shadow of its black hole, track stars whipping around it, measure its mass, study its flares, map its magnetic fields. We've learned to see in radio waves and infrared, to build Earth-sized virtual telescopes, to peer through dust and time and distance. We've learned to read the universe's subtle signals, the Doppler shifts of starlight, the polarization of X-rays, the gravitational wobbles of orbiting stars. And through all this ingenuity, we've come to understand that at the center of our home galaxy sits something that challenges our deepest understanding of reality. A place where space and time curve so steeply that they effectively end, where matter can enter but never leave, where the known laws of physics break down. There's something poetic about a black hole being invisible yet unmistakable. We can't see Sagittarius A directly. It emits almost no light, but its presence is written everywhere around it, in the stars that orbit impossibly fast, in the faint glow of superheated gas, in the occasional flares that burst from near its event horizon. It's there in the equations that describe how space-time warps, in the measurements that took decades to collect, in the blurry orange ring of the Event Horizon telescope's image. Sometimes the most important things are the ones we can't see directly, but which make themselves known through their effects on everything around them. Gravity itself is like this. We don't see it, we see what it does. Time is like this too, invisible but fundamental. Perhaps meaning is like this as well. We don't directly perceive it, but we see its effects everywhere, in the questions we ask, in the telescopes we build, in the patient, decades-long observations that reveal the dance of stars around darkness. So tonight, if you find yourself outside under the stars, looking towards Sagittarius, low in the southern sky during summer months if you're in the northern hemisphere, find the teapot of asterism, the pattern of stars that ancient astronomers saw as a centaur archer, but modern stargazers see as a cosmic teapot. The center of our galaxy lies in that direction, hidden behind clouds of dust, invisible to your eyes, but it's there. Sagittarius A, the sleeping giant, the quiet heart, the 4 million solar mass anchor that holds our galaxy together. You can't see it. You'll never see it directly with your eyes, but knowing it's there changes how you see everything else. The band of the Milky Way stretching overhead is a structure, not just a random scattering. You are part of something that orbits, that moves, that dances around a center. Even when you can't see the heart of something, you can feel its presence in the pattern it creates. And in the deep future, billions of years from now, long after humanity's gone, long after our sun has burned out, Sagittarius A will still be there. It will merge with another black hole, becoming something larger and more powerful. It will continue to shape the structure of whatever cosmic neighborhood it it finds itself in. Black holes are among the most enduring structures in the universe. Long after stars fade, after galaxies disperse, black holes will remain, slowly evaporating through Hawking radiation over timescales that dwarf the current age of the cosmos. They are, in a sense, the universe's longest memories. Everything that falls into Sagittarius A adds to its mass, changes its spin, becomes part of its history. Stars, gas, perhaps even other black holes over billions of years, all absorbed, all contributing to what it becomes. In that way, it carries the story of our galaxy within it, written in the only language that survives beyond the event horizon, the subtle changes in mass and angular momentum. So we end where we began, with something invisible that shapes everything visible, with a darkness that is not empty but full, full of mass, full of gravity, full of warped space-time and bent light and mystery.